there to there, that's about a 1.762 cantilever on the first floor. So that has to be seriously designed, to ensure that it can withstand the loads that it will be carrying. As a very significant cantilever, and then you have a column starting from there. The magenta column starts from the first floor and they move straight to the roof. Okay. Alright, so that's the first floor structural layout. The next we need to look at now is we need to look at the second floor structural layout. So we repeat ourselves. This is the framing structure arrangement. You frame your beam optimally, So if you look at the beam spans, you could see that here we have that is a 5.02 meter span, and this is a 4.25 meter span. Around that between 4 meters and 5.5. Okay, and then you see this cantilever, which we cannot do without. That cantilever is about 1.762. Okay, so it's very possible that the depth of this beam will be more than the depth of the beam we have, within the span. Okay, because of the high moment that will be anticipated on that beam. We will see how we would model all of these in staad. So this is the first floor structural layout. Let's move to the second floor structural layout and see what we did there. Okay, that's the second floor structural layout. Let's look at this in detail. Let's take away that. Now, if we look carefully, you would see what I was saying ab initio. Now, on the first floor structural layout, you have grid A. Let's look at it again. On this first floor structural layout, remember you have, I switched that off. Let's look at. Okay, so you have grid A. Remember, you have grid A. You also have grid 1. Okay, so it terminates at grid 1 and then at grid A. So what you see on this other side is the cantilever that the second floor commences on. So this is the cantilever of the succeeding floors. So that's the second floor. So that's the cantilever of the second to last floors, right? So this cantilever actually starts from the first floor, rather. So this is a cantilever on the first floor. So on the first floor structural layout, you will see the cantilever that projects away, right? And then you have these columns that start from the first floor, and it supports the succeeding floors above. So if you look at we're going to look at the second floor structural layout, you would see this grid A, rather A prime. So that's grid A prime. Okay, so this is the beam structural layout. So this is structural layout on the second floor. Okay, so when you develop your structural layout, you ensure your grading system is consistent with what you have in architectural design. It's very crucial. If you look at the architectural design, it has A, B, C, D, and so on. You make sure your grading system follows the same sequence, and then where you have additional structural entity, you indicate, it's best practice, you indicate with a similar letter that is similar identifier as that of what was shown on the architectural design for ease of construction and setting out. So we have A prime, B, C, C prime. We have a structural element there. That's what we call C prime. If you reveal the second floor structural layout, let's see. You would see C, which is a grid on the structural architectural layout. That's C, and then C prime is a grid on the structural layout because of the column that we have positioned there. There is no C prime on the architectural layout. Okay, so it has C, which are the major 225 walls, and then you have D. So when we include a column, we identify that as C prime, or we include a structural element, either a beam or a column, as the case implied. So use similar grading system as you have on architectural design, so that it can easily be referenced back to, and then you have a proper synergy and an alignment in structural design. So this is the first floor. So this is the second and third floor structural layout, right? So what we showed initially was the first floor structural layout, which had a cantilever. Second and third floor is typical. Architectural layout is typical. Structural design for those floors are similar. So you would see the columns that start from the first floor. You see them going up there. So you develop your structural framing properly. So you have your structural beams. So we have these structural beams. Remember that this column is starting from a cantilevered beam. Okay, so a continuous beam with overhang. That column starts from that, and is supporting this. So you could imagine there are kind of analysis that will be done on this beam, because this beam, all these columns are starting from the first floor. Okay, so you have the structural members, and then that's the structural beam, and these are the structural beams as well you have. So the first thing is to frame your structure, and then you have a void here. So if you switch off the architectural second floor structural layout, you have the void there. Remember I told you to develop your structural layout, you use the preceding and the floor, the preceding and succeeding floor to develop the structural layout of the succeeding floor. You use the preceding and succeeding architectural layout to develop the structural layout of that succeeding floor. So for the second floor, we use the architectural first. So you look at the first. So we use the architectural first and second floor structurals. But good thing, the first and second floor structure architectural layout rather are both the same. So to develop the second floor structural layout, you use the first floor and second floor architectural layouts. But the first floor and second floor architectural layout are both typical. So it's easy to frame the second floor structural layout. So you look at that, so we could see that, so we have those beams there, that beam there, we have this beam here, we have these beams, you position your beams as much as possible. Again, you try to frame your beams where you have your walls. It's good practice to ensure that your beams are properly hidden, so when people move into the building, they just do not get to see as much as possible any structural entity, to retain the aesthetic of the structure. So we have these beams. If you look carefully, most of the beams are hidden in walls, okay, except in few instances where it is impracticable to achieve that or uneconomical to achieve that, so you have it exposed. So you see, if I switch off that, you will see, you see that beam there, this beam 16. Look at beam 16, for example. You see beam 16 is in that wall, but it projects outside that wall on this location, so it's visible here because it needs to tie into this column here, okay, and it needs to be continuous, and it's also carrying this beam that's here that is picking up a column starting from the first floor. So as soon as you develop your structural layout for the floors, the next thing is to give your beams the proper mark numbers. Okay, so you give your beams, give your panels the proper mark numbers as well as your columns. So preliminary beam numbering system is subject to the structural framing arrangements. If your beam span are similar or identical, okay, and the members or the panels that are above and or that are adjacent the beam are of approximately similar configuration, the beams would have similar mark numbers. I repeat myself, in naming beams, because the loads that come onto the beams are being transferred from the slab panels up onto the beam. So if two beams or two or more beams are of approximately the same span, the same configuration, so if it's a 3 span continuous beam with an overhang, and you have another 3 span continuous beam with an overhang, and the spans of those beams are quite similar, and the slab panels that are adjacent to the beam, if for example this beam and this beam, okay, good, this is a typical example, this beam and this beam are both beam 16, because this beam is a 1 2 3 is a 1 2 3 span continuous beam. This is not a span, this is a point load coming to that beam, so it's a 3 span continuous beam. The slab panels are joining the beam on this and that side, right, and on this and this side are quite similar. So this is a two-way spanning slab. That looks like a two-way spanning slab subject to the ratio of the aspect ratio. So both will transfer similar load configuration, load intensities onto the beam, and implies that when you design this beam, you would have similar size and similar reinforcement for bending and for shear. So you will give them the same Mach number, so that when you detail this beam, the same structural detail covers for that beam. So this is your configuration. For your columns, you maintain the same philosophy: ab initio, preliminary. Columns that start from first floor terminate, ground floor terminate, and first floor should have a distinct Mach number from those starting from the first going to the second, or starting from the ground going to the roof, or starting from the third floor terminating, and all of that. So this is the philosophy that guides the structural arrangement. For your slab panels, your naming philosophy is subject to the nature of the slab. Now we have about 5 categories of slabs. You have solid slab panels, you have flat slab panels, you have reed slab panels, you have waffle slab panels. Okay, or you also have a composite type of slab panels. So solid slab panels are panels that have adjoining beams around them, such as what you have here. So when you're naming your solid slab panels, one of the key drivers is the fact that you check the continuity of the slab panels at the edges, as well as the aspect ratio. The aspect ratio is indicative of the nature of bending of the slab. If the ratio of the length to width, or the longer to shorter side of the slab, is greater than 2 by the specific requirement of the code of practice, that panel is considered as a one-way slab panel. Let's look at what the code states. Eurocode 2 firstly gives, we are designing this to the British Standard Code of Practice, but there's a very explicit definition of what a one-way slab panel is on Eurocode 2. It tells you that if a slab is supported, sensibly supported, okay, and it tells you that if a slab panel is supported on 4 edges, and then the ratio of the longer to the shorter side greater than 2, that slab panel is said to be, so we are looking at a sensibly rectangular slab panel. So a sensibly rectangular panel needs to be understood clearly in the right sense of its word. So if it is supported on 4 edges and the ratio of the longer to shorter side greater than 2, is taken as a one-way slab panel. However, when the ratio is less than 2, then it's said to be a two-way slab panel. Okay. So it explains what a one-way slab panel is. You look at the second definition. It tells you that if it possesses 2 free, unsupported, and sensibly parallel edges. If it possesses 2 free, unsupported. So if you have, for example, what this means is, let's look at the implication. If you have on a garage, okay, so if this is a garage, let's assume that, let me just take that. Okay, if this is a garage and then say you have a slab there, this slab panel is a one-way slab panel in this direction. Okay, it's not one way in the orthogonal direction, because this slab panel is sensibly supported in this direction, so it's one way in that direction. So the bending is normal to this plane in which you're seeing. So that's what the code states. So it states that if you have a slab member where it possesses 2 free, unsupported, and sensibly parallel edges, unsupported and sensibly, so you have, these are 2 free, unsupported, and sensibly parallel. So even if this inclines a bit, sensibly parallel edges, then that's panel is set to be a one-way panel. Okay, so this is just, you know, for illustration. So when you have slab panels, two-way, one-way, and then, you know, you want to give them Mach numbers, the guiding principle is that if the slab panel is similar, if the size, planned dimension of the slab panel is similar, and the continuity edges is similar. Remember, if the edge is continuous in that side, that side, that side, as in this case, for example, is continuous in 3 sides and discontinuous in 1 side, remember that the failure mechanism, the yield line failure mechanism, is such that you will have more loads, you know, onto the edges that are continuous as against the edge that is discontinuous. This is the requirement of the code of practice, BS 8110. Okay, so if the slab panel is continuous in 3 edges, the construction of yield line, one of the requirements of yield line construction is that yield lines form over the edges of boundaries, you know, and they form over columns, and they intersect, you know, between boundary edges. These are one of the considerations of yield line. So if you look at the yield line formation of this slab, you will find out that the loading from this slab, okay, onto this beam is so that you would have more loads, okay, on the edges that are continuous. Let's look at these things clearly. Let's look at what the code, where this thing is specified. Okay, just okay. If you look at this carefully, you would see that these are yield line formation. So yield line forms. So what are yield lines? Yield lines are the lines in which crack formation on a slab panel would first form. So where the slab panel or the slab material would reach its yield point. Okay, the location where you have formation of maximum moment, which will cause crack failure on the structure. These are the yield lines we are referring to. And it's on those yield lines that define how the loads will be transferred onto the beams that adjoin or bound that form the boundary on the slab panel. So if you look at, if you look at this definition, you see that, you know, if you look at this yield line formation, if you have all the slab edges to be continuous, we said that yield line forms at the intersection between, you know, yield. So yield line form, there are requirements for constructing yield lines. Yield lines form at boundary edges. So you have a yield line here. A yield line is where you have the moments to be maximum and where the potential for slab failure would occur. That's what we refer to as a yield line. So you have a yield line here, a yield line here, a yield line here, another yield line at the edges. Conversely, yield lines also form at intersection between boundary edges. So you have a boundary edge, so these are another yield line. These are another yield line, and yield line terminates at, you know, their intersection. So you see that this terminates there. So this automatically becomes the yield line formation. But if you have, look at this, if you have this to be continuous, and this is discontinuous, you see that you have more loads, okay, due to the formation of the yield line on the edges that are continuous as against the edge that is continuous. So this is exactly what we are talking about. The same thing as what you have here, and then what you have here. And when you don't have any support on the slab at all, you wouldn't have any load going to the beam. This is unsupported. So once you have no support, You have loads going to the locations of support and no load going to where you do not have support. So this is exactly the consideration you would take when you are specifying your slab panels. If your slab configurations are similar, you will give them the same MAC numbers, panel P1, P2, P3 as the case implies. So this is the second floor and third floor structural layouts. Okay, the next thing we need to look at is the roof structural layouts. What is the guiding principle? The guiding principle for your roof structural layouts is the roof configuration. You need to look at, so that's the roof configuration. Let's look at what has been done. Right, the roof structure based on the architectural design is such that the roof, we looked at it earlier on, but let's look at it more in detail. It slopes downward here, and this slopes in this direction. Let's look at section B. Section B, right? So it says it slopes downwards here, and that slopes, in that direction. And then the roof is to be slabbed, because you have, the roof is a very high structural entity from what has been done. This is 14 and that's 17. That's about 3 meters high. Okay, that's a significant height. And so it's carrying the roof structural members, the roof trusses and all of that based on the description. The pole lines, the truss, the struts, okay, and the ties as the case implies, okay, and it's slabbed. So you need to have your roof structural arrangement together with the location of the roof slab. So that's what we've done. So if you look here, the entire roof is set to be slabbed. So you will see that we have slab panels all around there. This is where the roof is sloping down. Let's take away the roof. Right. So it's slabbed all around here. There's a void here, so there's an access to the roof. The roof slopes in this direction, this slopes here, and that slopes here. Okay, so all of this is slab, and there's going to be felting around that to prevent moisture ingress into the concrete. If it's not well concretized, or even after a while, moisture could percolate through the concrete and it could affect the integrity of the structure. So all of the roof is going to be felted. That's the roof slab. Thickness of roof slab most likely is going to be 4 inches, and so on. So the next step you would have to carry out now is to model this entire structure in staad. Model this entire structure in staad. But before we do that, as a structural engineer, the next feasible step you would have to take is to carry out your load calculation. Structural load estimation for the building. Structural load estimation for the structure. What are the loads that the structure would carry? We need to look at this very, very carefully and intelligently. These are the very crucial aspects of structural design. The first thing you need to understand is to understand the code of practice requirement for loading structures. Now, this structure is a 4-story structure, and its height from the architectural design is, let's look at that, about 17.9 meters to the final roof level. So that's a structure that is going to be significantly affected by environmental loading. So the categories of loads that you would have to calculate for this structure is divided into 3 broad spectrum. 1, dead loads, or what we refer to as permanent loads, imposed loads, and then environmental load, which is wind loads. Okay, so environmental load is classified as wind load, loads that are impacted as a result of environmental conditions such as wave, currents, wind load. Those are for offshore structures, so wave load, current loads, hydrodynamic loads for offshore structures or bridges over water. And then you also have environmental wind load, gust loads, sustained wind speeds as the case implies. So we're going to calculate the loads. We're going to look at it very carefully. We're going to calculate the loads from the roof level up down to the foundation. So let's look at how this is done. So firstly, we're going to calculate the load on the roof level. The roof level load will be the dead loads, the imposed loads, and then the wind load. We'll see how we'll do that. Now, the guiding code of practice is the BS 8110 and then the BS 6399 part 2 for wind load calculation. The wind load calculation is going to be done in compliance with BS 6399 part 2, right? And then BS 6399 part 3 for roof loading on structures. BS 6399 part 1 is for imposed load on structures. You need to get yourself, used to these codes. Now, what are let's start with the roof level. So the first thing is your dead weights, your dead loads rather. So one of the dead loads that the roof is subjected to is the weight of the slab. Slab thickness is 100 millimeters. So we calculated that by saying the specific weight of concrete is 24 kilonewton per meter cube. So specific weight of concrete is 24 kilonewton per meter cube. So multiply by the thickness of the slab, which is 0.1. That gives you 2.4 kilonewton per meter square. Right. The next thing is felting. I told you that on the roof layout you are going to have felt. So this is the roof structure layout. You're going to have felting all around. Okay. So that's the roof structure because it's the roof and it's subjected to environmental effects like rain and all of that. So you need to have felting to prevent, to create an impervious layer. So 3 layers of felting, the self weight of that we are going to calculate. How did we get this? It's obtained from the BS 648. Okay, so that's BS 648. Good. So that's so it gives you different load requirement for different types of felt: fiber-based felt, saturated, sanded bitumen, as the case implies, roof felting and so on. So we are using this type of saturated bituminous felt, type 1A. So you pick up the corresponding weights, right, and then we're applying that in 3 layers. So that's the weight of felting. So you sum both of them, that gives you 2.5 millimeters square. So that's the dead load. So you keep all this load, you do a load calculation, because when you develop your analytic model, you're going to apply this load correctly with the right magnitude and the right direction and location, so that the load impact is felt properly by the structure. Next thing is imposed load. Now this roof, let's see the architectural design. Okay, just look at the